In this part, I would like to introduce the first active device. When we call active device, okay, we usually mean that it can amplify signals. And that means that usually we have something like this. We have an amplifier, and if we have the x of t, it means we have the amplifier, means that it can be multiplied by a factor. And for the A, we'll call it a gain. Okay, so this is active device. And the bipolar junction transistor is the first semiconductor device that can amplify things. And in the past, before semiconductor, we have vacuum tube. Okay. The concept is pretty much the same between bipolar junction transistor or MOSFET and the vacuum tube. Okay, so once you understand one of that, you can try to learn the other two. Although in this semester, I will also introduce MOSFET, which called field effect transistors. But let's talk about the bipolar junction transistor first. If you remember, okay, in the past, we talked about the diode. Let me review the diode. We have diode, something like this one. And we have P, we have N. Okay. And because we have the P and N connect together, so we have something called the PN junction. And if you still remember, if you apply a voltage here, V has to greater than around 0.75 volt, such that the current can flow from this part to this part, right? And then we have the equivalent model called the transistor, a diode called it is 0.75 volts, and this is R, and this R is usually very small. But as we said before, a diode is only good for example, is one of the application is to add as a rectifier. But how to amplify things? This amplify or amplification is something very important in today. We have to make this signal larger. For example, if you want to measure your skin conductivity, if you want to measure the electric signal of your muscle, if you want to measure the electric signal of your brain, those signals are very small. For example, they usually less than 1 millivolt. And 1 millivolt is definitely too small. So usually we have to magnify it to, for example, 1 volt. But 1 volt, from 1 millivolt to 1 volt, is the gain has to be over 1,000. So we need to have something to amplify a signal, those very small signals. Okay, that's one of the application of the amplifier. And the bipolar transistor, bipolar junction transistor, is a major modification to diode. And as we can see here, we have diode here. Actually, we have diode here, and we have another diode here, right? So we have two diodes. Okay. And as we see, once you have a diode, then you are going to have a depletion region, right? So we call this one this part is depletion region. We have the depletion region here. And this is called depletion region, right? And this depletion region, okay, prevent the current flow through it. But in order to eliminate the depletion region such that the PN junction can be conductive, then we have to apply a signal which is greater than 0.7, right? Okay, so that's the whole idea of this. And people are thinking about how to amplify things, and that and the transistor provide a very good way to do it. We want to have something, for example, if this is the, sorry, I should use this one first. If we have a very small current, which calls IB current, because I current, is it possible that this very small current can induce more current flow through it here? So this is what we call the IC, and we want the IC is greater and greater than the IB. So if IC is greater than IB, IC is greater than IB, then we say the input signal is multiplied if IC can be beta IB. And so let's reflect the last sections and last part of this course. Remember, it's something like this one, right? It becomes a control source. We have I input here. If this I is called IB here, then we can generate a new current IC, which is much greater than IB. And if we can form this kind of relationship, then this source is controlled by this source. So for bipolar junction transistor, it's a source control current source. Okay. That's the reason I put the control source at the end of the previous part. Okay. And then people want to say, if we have the one direction of the flow, can I provide the other direction? So two types of the transistor were invented. One is this one, we call NPN transistor. This is called PNP transistor. And it has three terminals. One is called B, which is base. One is C, we call it collector. One is E, we call emitter. Okay. So this one is an NPN transistor. So in order that the transistor to function, we have the BE junction here. We have the B, we have E. So we call this one is the BE junction. So this part is the BE junction. That's why we call it junction transistor. And as we know, because this part is a depletion region, and the P here, the P, this part, P is very thin. Sorry. So this one is, this figure is not draw proportional to the real transistor. Okay, actually P is very small. If I can rewrite this one, I say, okay, this may be the N, this may be the N. So this is N, this is also N, but P is very small. P is only slightly here, very, very small. Okay, this is P. So once I apply, once I apply the VBE, this VBE means that I have a voltage here, and this VBE is greater than 0.7 volts. Then the depletion region disappear. So the depletion region disappear. And because it's very, very thin, because the P part is very, very thin, and this part, this part complete disappear, because there will be no depletion region here, because before that we still have the depletion region here. But because the VBE, the depletion region disappear. Depletion region disappear means that the P almost non-existing. Although we still have a P here, but because it's very, very thin, so the current can flow through from the N through the P and through the N. So the whole idea is that the P must be very thin, and that the depletion region is easily be eliminated by apply the VBE, which is greater than 0.7 volts. That's the whole idea. And the best of all is that when it's conductive, and this one is IB here. Let me eliminate this one. We have IB here, and the IB, we have IC here. Then IC is beta IB, which is controlled by the IB. So IC become a control source. And we have the IE here. IE, it turned out it has to obey the KCL. So IE will be IC plus IB, and which is equal to beta plus 1 IB. But usually beta is quite big. For example, beta can be 20 to maybe 500. Very, very big. And the beta, the size, how much is beta depends on the density of the electron doping to the material. Okay, so this is the one. So now becomes, we have the something that we can amplify things. Okay, so there's a figure, something like this one. So that means the BE here, well, originally is something like this one. This is something like a switch, and you apply a VBE, and we have a switch. Turn the switch on, and so that the current can flow through it. Okay. This is the source, but actually this one is not current voltage control current source. It is current control current source. But in this figure, he says that because the IB current is controlled by this one. So you may also say it's voltage control current source. But I would like to say, but most of the time when we use it, I would like to say is current control current source instead of voltage control. Although the IB current is dominated by this formula. and this formula is also dominated by the VBE. Okay, and we have two types of the transistor. It becomes a pair. So we have NPN, this one. So for the NPN, the B junction should be greater than 0.7 volts, and so that the current can flow through it here. But for the PNP transistor, it works reversely, and here VBE must be smaller than 0.757 volts. Means that we need to have a battery, something like this one. This VBE is minus VEB, and this one has to be less than 0.75 volts. No. Sorry, it's minus 0.75 volts. Minus 0.7 volts. Okay. So we have two kinds of transistor. And let's look, after we learn about the characteristic, the working theory of the transistor, we can look at some of the example spec. Okay. This is the example spec of the bipolar junction transistor. Okay, you can see. This is the one you see it. Okay. And it will tell you, usually you see this is the half circle here. Okay, and half circle you indicate the 3 pin, and EBC is the 3 pins here. And there are some figures that you need to understand. The first of all is this is the figure. It's called the collector emitter breakdown voltage. Means that the CEB means that the VCE cannot be greater than 40 volts. Okay, this is a very small transistor. If you apply high voltage, okay, the things will break down. And this will be collector, and the base breakdown voltage is 60 volts. Collector here, VCB. And we have a VEB. This is the emitter base breakdown voltage is 6 volts. So this should not go over 6 volts. And you have some cut-off current. Cut-off current is very, very small. It's 50 nano ampere. Nano stands for 10 to the minus 9. Means that if the IB current smaller than 50 nano ampere, then the transistor is regarded as turned off. And one of the most figure that we have to care about is the HFE, and which is the beta we talk about. And as we see that the beta can never be a constant, as you will see, it has a spec, something like this one here. For usually we use this kind of transistor, we use it mostly around 1 milliampere. So we'll see operating at, for example, 27 degree or 30 degree, and when VCE is 1 volt, okay, when VCE is 1 volt, and when IC is 1 milliampere, as you can see, the beta is 70. Which means if IC is 1 milliampere, then the IB current will be 1 milliampere over 70. Okay, which will be 1.4. Will be is this 1,000 microampere over 70. So this one will be around 14 microampere, which is very small. Okay. But as we can see, the beta can never be a constant. When you operate in different kind of conditions, okay, the beta changes. So you have to be very careful when you design your circuit. And this one, This one is the minimum beta, and this one it would be maximum beta. And why we have the 100 and the 300, the difference is over 200%. It's because that although you have the same transistor, same transistor of this, for example, this is, I believe, 3904, I believe. And when it is manufactured, okay, before the process will arrive, so it is possible that it already it should be 100, but it turns out to be 300. But usually the beta will be in this condition, the beta will be between 100 to 300. Okay, so you have to design accordingly. So that means that bipolar junction transistor is not a linear device. When we call it linear device, is that if we have IB, no matter what IB is, okay, the IC should be, no matter IB is, then IC should be beta IB. But unfortunately, the beta is not fixed. That's the problem with the bipolar junction transistor. And if you ask me about what about the other device, all the device in this real world act something like this, it is not fixed. Okay. All right. So I first let you understand the bipolar junction transistor, and this will be the bipolar junction transistor characteristic. For example, if you can remember that this is the characteristic curve of your diode. But now we have a much more complicated characteristic curve of a bipolar transistor, which we will talk about it in our next class. Thank you.